So in this lecture, we're actually going to start implementing time series forecasting. These slides are posted on LMS, and there is a kind of a long set of slides. And so through this set of slides, we're going to implement appropriate time series forecasting methods for data with different combination of systematic components, which you learned last time. If you look at your historical data, you should first identify what systematic components are in it, and then map it to an appropriate forecasting method. So if you're following along in the textbook, this is chapter 7. However, we're going to use R and RStudio instead of Excel. And the set of lectures will use R files that are posted on LMS. So as a reminder from last time, the steps of statistically forecasting time series data takes this following form. The first is that you should plot your historical data, because a major assumption of time series data is that the past is a good indicator of the future. And so our goal here is to identify what patterns are happening in the past, and then make sure that our method captures those patterns so that they are captured in our forecast of future demand. So once we've identified the systematic components, in this class, we're only going to look at level, trend, and seasonality. If we identify that our data has only level, then moving average or simple exponential smoothing are a couple methods that we'll learn in this class to apply. By no means is it the only methods. Want to be clear, there are other methods, but these are appropriate forecasting methods. And then once you have selected an appropriate method, we need to actually create a forecasting model. And that's what we're going to do in this set of lectures. And so what does it mean to create a forecasting method? For the simple stationary series, we need to figure out basically setting parameters. So for moving average, that would be number of periods. For simple exponential smoothing, that would be how should I set alpha? And these values will make more sense as we go over them in the slides. For methods that capture trend and level, but no seasonality, we need to set alpha and beta. And so forth. And so this creating a forecasting model is how should I set my input parameters? Once I have created my forecasting model, I then should use it, right? So I'm going to use it to predict something in the future, and then the future happens and we observe what happens. And so we assess what I predicted versus what actually happened, and see if we need to adjust and revise our model. And because we're doing adaptive time series, we will update our estimates for these systematic components and then continue along. So this may be, if you're new to this, seem a little bit abstract, but we'll go through this, walk through this, and then with the power of software such as R, it'll kind of automate this process. All right, so let's get started with the simplest time series, which would be a stationary series. So the idea here is the only systematic component would be level. And so here's an example of some data that you could see. There's definitely variability over time. It's not perfect of what's going on, but there doesn't seem to be a trend. There doesn't seem to be seasonality. And so, this would be an example of some data sets that would be appropriate to consider as a stationary series. So in general, a stationary time series is kind of the general form, okay? So what we have here is basically a form that has one systematic component, that's the level, and then it has an error term. And on expectation, we want our error to be 0. We don't want it to, but over time, it'll vary up and down, right? So on average, we would be at that level, but there would be variation or noise associated with that. So again, the only systematic component found in a stationary series is the level. And in this class, we'll study two methods. You've likely maybe seen these before. Moving average and simple exponential smoothing are both appropriate methods if you have a stationary series. So let's get started with moving average. Again, likely you have seen this before. It's just a series of arithmetic means. So what we're doing is we're saying, okay, we want to give equal weight to the n most recent observation. So you may have seen a 3-week moving average, a 7-day moving average. That's what this is. And so what does that mean mathematically or kind of notation? Again, the only systematic component in this data is level. So we need to create an estimate for level. And how we're going to do that with the moving average is we're going to take the last n periods of data. So remember, as notation, D of t are the things that actually happen, right? So D of t, we are at time t, and I'm going to go back n periods, and I'm going to just take an average of that, okay? And that will give us our estimate for the level at period t, which we're going to call L of t, okay? So you've likely done this before, seen this before, just kind of getting you associated with the notation, okay? So in doing that, we haven't forecasted anything. As you will note, D of t happened. We have observed data. So getting L of t, we haven't forecasted anything. So how do you forecast something using a moving average? We basically say, okay, we get L of t, and then that will be our forecast in period t plus 1. And if we look out further than t plus 1, our forecast is still L of t. And so you may ask, okay, a couple things I want to point out is that you need observed demand D of t to calculate L of t. So a lot of times in homework and exams, people are like, when do I use L of t formula? When do I use F of t? The short answer, and we'll get into more details and go through the code in a follow-on video, but the short answer is you basically keep calculating L of t as long as you have observed data to do so. But you can't calculate L of t if you don't have D of t. And we'll see that again in this lecture and in future lectures. The other thing I want to point out is this M period in advance forecast. If you notice, F of t plus M is equal to L of t. So what does that mean is I have the last piece of observed data in period L of t. As long out into the future, I'm going to predict that it'll be L of t. And so it's not updated, it's a flat line. Okay, so you may say, why would I do that? I want to remind you that this is a stationary series. The only historical data in terms of systematic components was level. So the only thing in the past we knew was that it had level. So our best guess into the future is the same, is level all the way into the future. Okay, so you do that, and then, you know, the future happens. You observe what actually happens in D of t plus 1, and then you would update and adjust. You would get a new L of t plus 1 estimate, and this process would continue. All right, so let's do that. So, you know, let's just take an example, 3-month moving average. And so if you look at, just to kind of orientate yourself with this table, we have months T, we have actual sales data, D of T. So these are things that actually occurred, right? So we are standing, July just happened, and we have this observed data, okay? L of T, again, as I defined on the previous slide, is our estimate for the level. And so if you want to think about how do we get that estimate? Well, this is a 3-month period moving average. And so I basically stand here, D of 3, and then I say, okay, I need 3 of them, go back, and that would be 11.67. Okay? And my forecast is just one period. F of t is L of t minus 1. Okay, so in April, my forecast for April is just my L of March, for example. And so we can then keep doing this. As you can see, there would be a pattern. And so computationally, it's really good to use computers, Excel, something like this to do this. And so if you see, where did we get L of April? You can see, okay, we need to go 3 months back and take the average. And then there's always a 1 period lag between F of t and L of t. Okay? And so my question for you is, what is the forecast for August? So please tell me, what is the forecast for August? And I would like you to pause the video, do your math, and then come back and see if you got the right answer. So hopefully you figured out that the correct answer is actually B, 22 2/3. How do you get that? Well, that's basically the sum of 26 plus 23 plus 19 divided by 3. And that is the forecast for August. So the correct answer is B, 22 2/3. All right, awesome. So now I'm going to ask you a different question. So to note, we have not observed anything. The last observation of data we have is in July. So D of 7 is our last piece of data. So I'm standing at, you know, let's say August 1st. And I now want you to tell me, what is my forecast for September? Again, please pause this video, think through it. So what is your forecast for September? This one actually requires zero calculation. So this is just applying this equation, m periods in advance is just f of t plus m equals L of t. So as you can see, our last L of t that we can calculate is in July. And so it doesn't matter that we're 2 periods from July, we still get that the answer is 22 and 2/3. So again, the correct answer here is B. If you were wanting to write down and try to recalculate the next, August's L of t, so L of August, you are unable to do that because you don't have D of August, okay? So please remember, no matter if I asked you, what is the forecast for September 2025, the correct answer still would be 22 and 2/3. So all the way into the future, we assume it's whatever the most updated level estimate is. Of course, once we observe the demand for August, we would update our estimate. But into the future, because again, this is a stationary series and the only systematic component we have is level. Okay, so hopefully that makes sense. And so hopefully you got that both the forecast for August and the forecast for September, given the last piece of data we have observed occurred in July, is 22 and 2/3. All right, so one thing to think about is as you go into the future, and one of the kind of harder things sometimes people get their mind around is you have D of t, which are actual pieces of data, and then the forecast, which here we need L of t. We can do that forever, right? So how often do I have a forecast? I have a forecast into the future forever because you can think about just M keep getting bigger and you can forecast. All right, so this example used n of 3 months, right? We had a 3-month moving average. I could say, why did I decide for 3 months? What if I used a 2-month moving average or a 5-month moving average? What does happens if I increase n, which is the number of things I'm dividing by and the number of pieces of data? So what happens? What happens is we increase n. So here's just an example. D of t is the demand. So this is what we actually observed. N of 3 for this data, if I use the moving average, you get the pink line. And if I do N of 5, you get the yellow line. So I want you to look at this graph and say, okay, what's the difference between the pink line and the yellow line? One of the things you can say is that the yellow line is more smooth, right? It doesn't adjust to as much changes, right? And you can think about this mathematically. What is the difference between t and t plus 1 of our estimate? In the 5-period moving average, 4 of the data points are the same. I'm just kicking out 1 and adding 1 in new, right? So 4 of the data points from one period to the next stay the same, and I'm just adjusting the last one and the forward one, right? With a 3-period moving average, you're again kicking this guy out and adding 1 over here, but you only have 2 points that are the same, right? So what does n do? As you can think about, as n gets bigger, it levels things out, it smooths things out. As n is smaller, it isn't quite as smooth, and there are adjustments to that. Okay, so that's kind of conceptually what is n doing. But then the bigger question is, okay, great, like I can kind of understand that intuitively. How should I set n? Should n be 3-period moving average? Should be 13-period moving average? 5-period moving average? They're all stationary approaches. They're all appropriate. So how do you determine n? And this actually gets to the next step of our forecasting steps. And so this is creating the forecast for moving average. That would be selecting n. So what you need to do is we need to measure the forecasting error. So in theory, we would measure it for any, n-period moving average, and as well as any other like stationary forecasting methods. So you'd basically say, come on, all these forecasting methods that are appropriate for this data set, let's compete, okay? So come compete. I want you 2-period moving average and you 3-period moving average, and maybe, simple exponential smoothing, you're also an appropriate stationary method. Come to my competition, right? And so what is that competition? We are saying, I want you to figure out who can have the smallest forecasting error. Okay, that's my like goal of my game, right? And so, what we want to do is we want to make sure that this competition is fair, right? And so, to be able to be fair is we need to make sure everyone's playing on the same playing field. And before we even get to that, we need to say, okay, how do we even calculate forecasting error? If you remember from the previous video, we basically said you can't calculate a forecasting error unless you have what actually happened and what you thought was going to happen, right? So you need both, and the key word here is both, observed data and the forecast. Okay. And then to be fair, you want to have the most cool long-term competition, right? But you need to make sure everyone's playing on the same footing. And so usually what that is you say whatever subset is the biggest that everybody has both an observed and a forecast, you use that as your competition kind of rules. And then you pick the one that has the smallest. And you will get an opportunity to do this in your homework. And so if you're using R, and we're doing this specifically for a moving average, you would implement this in R code using a for loop. Okay. All right, so that's how you would determine how to set n. Let's use an example to see if you got that concept. So here's the same data I showed you before. And below my question is, which periods do you have all the data you need to calculate the MSE, the mean squared error, for the one step ahead forecast? And I provide the equation for that there. So please, if you need to, pause the video and really think about what's the answer to this question. All right, so hopefully you picked D. D is the correct answer. And the key thing here is you need both the observed, the actual sales for this example, and a forecast. Okay, so where do you would have periods for demand from periods 1 through 7. And you would have a forecast starting in period 4 going off until infinity, right? So you have 4 to infinity for the forecast and 1 through 7 for the actual or observed observations. So you need the intersection of those 2 points. Sets of points. And so what are the biggest collection of data points where you have both of those? That would be 4 to 7. So if you were trying to compute the biggest data sets that you would actually have all that, it would be from 4 to 7 for this example. So D is the correct answer. All right, so then my question, hopefully you're being kind of a critic, is, okay, great. I just 4 to 7, one of the observations about 4 to 7, guess what? 4 to 7 already happened. That's in the past. So you could be like, okay, great. Like, why the heck are we forecasting something in the past? Why the heck are we calculating something in the past? Like, isn't my goal to forecast the future? And so to that question, I think it's important to think about what are we using MSE for, or these errors of measure for. And so, these other measures of error, or MSE, are used to determine what's the best forecasting method and to set parameters. So we would use this, we'd calculate MSE for, let's say, a 3-period moving average, a 4-period moving average, a 5-period moving average over the fairest data set. And then we'd say, which one of you has the lowest MSE? Okay. So that's, we had picked moving average was our forecasting method, but then what are we doing? We're setting N, and that's what, why we would do that. Okay, so an example is a 3-month moving average, a 4-month moving average, or an exponential smoothing with alpha 0.2 better for my specific stationary data. So a key thing about this bullet point is all of those are appropriate methods. They're all stationary methods, so they are all appropriate for my stationary data. But then the question is, who wins my competition? And so, methods for comparison should fit your systematic components, and there are many of them, even way beyond what we're doing in this class. And then, okay, so let's say doing that competition, let's say a 4-month moving average was the best. They gave me the lowest MSE. Then we would say, okay, we're going to use that. We are going to use a 4-month moving average for our future, and we're relying on our assumption that the past is a good indicator of the future. And we're going to put our best creative forecast to work. And so the key thing here is which method, moving average, and what parameter setting, n equals 4. into work. So hopefully that makes sense, because here's my last for this video clicker question. So my question to you is, how do you determine whether a 3-period or 4-period moving average is better for your data set? So I'll let you kind of pause, hopefully read through this, and then hopefully get the right answers. So hopefully, as you've read through this, you picked A. Okay, so what does A say? Is it says to measure the forecasting error for both methods on past data. The key of why past data versus future predictions is you can't measure a forecasting error on future predictions because you don't have the observed data. So the only way you can measure forecasting error is if you have what actually happened. So C and D therefore are wrong because you can't measure a forecasting error on future predictions. That's just not possible. So A and B are now, kind of our competitors. And so the difference is, do you pick the one with the smallest forecasting error or the largest? You want to minimize the difference between what you think are systematic components and that error term that we started this video. So A is the correct